also health record. And the speaker is Anindya Antar from University of Michigan. Okay.
Hi, my name is Anindya Antar. I am a PhD candidate in Computer Science and Engineering, University of Michigan. Today, I am going to present our work on behavior modeling approach for forecasting physical functioning of people with multiple sclerosis. Highly functioning people with MS, a chronic disease of the central nervous system, experience few barriers to social interactions and professional careers. Functioning indicates people's ability to perform daily activities. For example, lower extremity functioning indicates the ability to use legs for activities such as getting out of bed, whereas upper extremity functioning indicates the ability to use arms such as brushing the teeth. Forecasting functioning before it worsens could enable just-in-time clinical interventions, such as day planning that allows people to plan their day in advance, and activity pacing to balance daily activity intensity and rest. It is challenging to track and forecast functioning outside of the clinical settings because MS symptoms that influence people's functioning are often variable, unpredictable, and fluctuate over time. Also, people's demographics and patterns of performing activities may influence their functioning. Existing ML models trained on in-situ data can predict the most likely symptoms and functioning levels that people are currently experiencing. However, these models do not forecast the trends of changes in MS symptoms and when people will experience low functioning ahead of time. Here, we present a human-centered behavior model to forecast end-of-day functioning of people with MS. A key novelty of our approach is the incorporation of domain knowledge from an expert who is a clinical psychologist, both during feature engineering and model evaluation. We performed both quantitative and qualitative evaluation to show the implications of accurate forecasting. Our method has many steps, so I will try to break them down one by one. We used an existing time series dataset collected by MS clinicians that contains wearable actigraphy and self-report data from 107 people with MS. We then co-engineered features with the domain expert that describe behavior instances of people with MS in different situations and actions. For example, situation features may describe who these people are, such as their gender, age, what type of MS they have, and whether they use any mobility aids. Also, situation features describe the time of day when self-reported symptoms such as pain and fatigue values were reported. Similarly, different features describe the actions people perform at each time step. For example, people's activity intensity, frequency of breaks, and whether they report their pain and fatigue. We track missing self-report values as they may suggest people are feeling symptomatic, busy, or forget to charge their watch. And then once they perform an action, they move on to the next state, here morning. Then they perform another action and move on to the next state. This process continues for the rest of the day until they perform the last action and reach the end of the behavior instance, when we can finally estimate the conditional probabilities of different functioning levels and forecast the one with maximum probability. Next, we illustrate our modeling approach by representing the behavior instances in a Markov decision process. Our final behavior model has two components, a Bayesian network and an inverse reinforcement learning model. So, the first component is estimating the state transition probability given the current state and action, which we modeled using a Bayesian network. This Bayesian network computes the joint probability of changes in MS symptoms and functioning given all other feature values. We also estimated the probability of performing different actions given a current state using an inverse reinforcement learning algorithm. Then we validated our model in a series of quantitative evaluation. First, we performed feature ablation experiments to find the most important feature. Then we validated our model's ability to predict next interval symptoms and functioning. This is an important intermediary step to predict a sequence of symptoms throughout the day and forecast people's end of day functioning starting from any daytime interval. We compared our model with 16 off-the-shelf ML baselines where we did not incorporate any domain knowledge to modify and engineer the features. Our model outperformed existing ML baselines in predicting next interval pain and fatigue levels, with most errors observed at the boundaries between symptom levels, particularly when individuals prefer to report medium pain and fatigue. Despite such symptom prediction errors, our algorithm, which uses probability distribution over various symptom levels instead of just the most likely ones, led to 21% and 29% improvement for predicting lower and upper extremity functioning. Next, we evaluated the model's capability to forecast end-of-day functioning using both self-reports and actigraphy to support timely interventions, as well as its ability to forecast functioning with only passive actigraphy, reducing the need for repeatedly collecting self-reports. Results showed that our algorithm can forecast end-of-day functioning starting from any daytime interval, even as soon as when people with MS wake up. This can enable timely notifications for people with MS to better manage their symptoms and activities for the rest of the day. In our second experiment, we found that our model could predict functioning given only passive actigraphy data without repeatedly asking for self-reports. However, model performance started decreasing when afternoon and evening actigraphy data were missing, suggesting that end-of-day functioning is closely associated to the activities people perform in around the time of those self-reports. Finally, we conducted qualitative visual exploration to identify model limitations in hypothetical what-if scenarios suggested by the domain expert. We created these scenarios using static Sankey visualizations and compared model-generated samples with data. One such scenario is to understand how people's progressive MS subtype and usage of mobility aids influence model forecast of lower extremity functioning. According to the data, people with progressive MS subtype are more likely to use mobility aids. However, the model could not capture such relationship from the data, indicating a lower likelihood for this joint probability. Although such error did not affect our model's prediction and forecasting abilities, because we set these two feature values from the data as initial state variables, this may potentially lead to reduced performance in other evaluation experiments that we did not examine. To summarize, our human-centered model captures behaviors of people with MS to forecast people's functioning, which is an important prerequisite for recommending timely intervention. A key novelty of our approach is incorporating domain knowledge from an expert, which resulted in a more accurate model than existing ML baselines. Our evaluation showed the value of our engineered features and the ability to visually debug model errors that were otherwise difficult to spot using solely quantitative evaluation. For future works, our results point to additional features that could further improve the forecasting performance. For example, considering sleep quality, activities of daily living, and collecting actigraphy features at a finer granularity. There is also scope to improve forecasting performance to transfer clinical knowledge across diverse MS population, promoting broader adoption of ML. Finally, our forecasting method has implications to support future behavior-aware user interfaces that deliver just-in-time interventions. Thanks a lot for listening to my talk.
Any questions? Okay.
Hello, quick one. I was just wondering, you talked about lower limb functioning and upper limb functioning, right?
Yeah,
and
yeah.
then the data that you collected was only with, at least in the image that you showed, was just a device that seemed to be a wrist-mounted device.
Mm-hmm.
And so can you talk a bit more about how you were able to get to, for example, lower limb functioning? I guess you talk about mobility in terms of walking and upper body. You were talking about maybe doing hand motions and movements. So I was just wondering if you could talk a little bit more about how you actually got to the functioning upper body and lower body.
That's a great question. So the device that I showed was an actigraphy watch from where we are collecting their continuous activity data, and also it asks you to self-report your symptoms on a scale of 1 to 10. But for the functioning report, that's the end of the diary measurement. So clinicians provided them with a series of questionnaires to like answer how well you could perform activities such as getting out of bed or getting out of a car or pushing open a heavy door, rate on a scale of 1 to 5. So then they perform an average assessment on those questionnaires, and from there they reported the final functioning measurement, which we categorized using entropy-based supervised binning into low, medium, and high functioning. So the functioning values are not coming from this watch. That is a separate measurement that patients reported at the end of the day.
Got it. Thank you so much.
Yeah, thank you.
Let's thank speaker again. Okay, the next one is power speech in the wild. It's basically to analyze audio, collected from the